Hi everyone, so I'm Ben and I'm currently a master's student at the University of Victoria, and I'm just going to give a quick talk on a little SDR project. Okay, so first off, the motivation for this, we had a talk earlier about this modular CubeSat radio we're working on, and the main takeaway for this talk is we're basing it off of the open source Hermes Lite-2 SDR. It's kind of a bit of background. It's an HF SDR, and it's just like a direct digital conversion SDR. And the main limitation we kind of needed to overcome is the transmit bandwidth on it was only 48 kilohertz, and that's just based on like the duck chain in the FPGA, so it can be changed. So that's kind of what I did for this little project. So first off, a little bit of background. Probably can't make out too much of the details on that, but the rough idea of how the existing DSP chain on the Hermes Lite works is you feed in like a 48 kilosample a second IQ signal, run it through some interpolation filters, run it through a mixer and NCO to like frequency shift it to the output you want, and then that gives you about a 80 megasample a second real signal that you send out to a DAC. So kind of main motivation, probably most of you have an idea of this, behind interpolation is you want to get rid of spectral images, sort of like analogous to aliasing when you're downsampling. So if you just upsample a signal without doing any filtering, you get some spectral images. So you basically need to add a low-pass filter, but you're running these filters at pretty high rates, so you want to do some optimizations. Kind of the first thing you can do is do a polyphase FIR filter, which basically, since after you've interpolated your signal, a bunch of the samples will be zero, so there's not much point in computing the values of them. So the polyphase filter is just kind of a clever way of not doing those zero multiplications. So you can reduce your number of multiplications, and like as a result, the FPGA resources you need by quite a bit doing that, but you still need a fair bit of stuff because if you have a high rate signal, you're still doing a lot of multiplications. So usually you can do the bulk of the interpolation with a CIC filter, which is basically just like a boxcar or moving average filter. So an FIR filter where all your coefficients are 1. And that basically means you don't have to do any multiplication, but the cost is like the frequency response is pretty bad. You've kind of got a not very flat pass band and wide transition band, so you need to do some initial filtering. So kind of with that in mind, what we actually did for the Hermes Lite was, it's fairly easy to adjust the filter rate. You basically just take the CIC filter, reduce how much it's interpolating by, so you get basically a wider bandwidth. So basically reduce the interpolation factor of the CIC filter by 4, and then before that you've got a polyphase FIR filter. And just to kind of keep the hardware resources the same, I reduced the length of that filter just because the FPGA was pretty full. So you end up with like a quarter the filter, a quarter the length as it originally was, which just kind of keeps everything the same in terms of processing requirements. Of course, the cost of that is you have a slightly wider transition band on your low-pass filter, but that worked out fine for us. So kind of one sort of interesting thing you have to do with your FIR filter, it's not just regular low-pass filter. You want to add a bit of droop compensation, since you could see previously the CIC filters have sort of like a sync-like response. So you want to kind of make the pass band of your low-pass FIR filter the inverse of it. So you can see on the left there, we've got the pass band of just the FIR filter. On the right, it cascaded with the CIC filter, so you've got a flat pass band. And then if you kind of implement that all in the FPGA, run a frequency sweep, you can sort of see what happens. So if you just do it on the left without an FIR filter before your CIC interpolation, you can kind of see you get the results you'd expect, a bunch of spectral images and kind of this. You can sort of see the top of the sync-like response of the CIC filter. Then if you add in the FIR filter, get kind of are increased about 200 kilohertz bandwidth, so 4 times the 48 kilohertz, and the spectral images are all suppressed. So that's all I've got, pretty short presentation. There's a GitLab link there that has the modified FPGA gateware and a modified GNU radio block for it. If anyone uses the Hermes Lite and wants a wider transition bandwidth, you can do that. So anyways, thanks all for listening. That's all I've got. If there's any quick questions, I can probably answer it. Otherwise, I'll hand it off to the next person.